Hello, this is a recap of Unit 7. We've got a lot of problems to go over today, actually. Probably a little B2 video worth. You can take a look at your ranking. You're feeling pretty good about it, actually. 4s, and then as we get down, we move into more of the 3s. But that's pretty good, because 3 just means you got to look over it again. So not too bad. I've got a few things to go over. Looking at for the video on Thursday, the best time seems to be 11 a.m. and then noon. So I'm going to do it at 11 a.m. These people don't care. Hopefully that can make what most people can make. I'm going to record it anyway, so if you can't make it, that's okay. We'll catch you another time. I'm going to do more like in class, like all of us kind of together asking questions sort of stuff in the future, like next week and the next week. So this won't be our only time. Then here's where we're sitting on how well we did on these ones. What I'm going to go over is the top ones that didn't go so hot was 4, 8, and 13, but other people requested other ones, so I'm going over 3, 4, 7, 8, 9, 10, 13, 15, and 16. So here we go, number 3. Here. Okay. So this problem is about, is this at equilibrium or is it not? The answer to it is B. I'm showing the answers as we go. It's not possible to determine the system has reached equilibrium because amounts of x, y, and xy have changed. That's a true statement. But why isn't A, B, A, C, or D not right? So if you look at A, this is talking about the amount of what kind of stoich we have. Knowing the stoich doesn't tell us if it's in equilibrium or not, so that has nothing to do with it. C isn't a good answer because it talks about the rate of formation of xy as constant. For one, the pictures don't show a constant rate in which it's being made. And two, just having a constant rate doesn't necessarily mean it's at equilibrium. It could be constant for a while and then a dip down, and it just means that it's constantly fast or constantly slow, but it could be constantly fast and then it tapers off and then you get equilibrium. You can't say the rate of formation being constant is it. And the picture doesn't actually show that anyway. Same thing for D. That's talking about X and Y. The pictures don't show a constant rate at each part. So that can't be the right answer either. Okay, moving on to number 4. What we're talking about here. Okay, so this is the equilibrium values that they have. And it says if the experiment is repeated at a higher temperature, number K changes with temperature, at which the K is larger, which of the following best describes the effect of the temperature? So if K is larger at a higher temperature, that means the reaction proceeded towards the products, towards C. So if it proceeds towards C in order to make a greater K, that means we have fewer A's and fewer B's and more C's. So looking at that, A is not a good answer because it says everything gets more. That's not true. B is not a good answer because it says A and B remain constant, but C will change. That's impossible. If you're going to change C, it's because A and B are being used up. That doesn't work. And D is not a good answer because we're not increasing the amount of A and B, we're increasing the amount of C because it's going towards the products. So that does not work. That's why the best answer is C. Moving to number 7. Somebody had a question about the notation on this one. I'm writing down the times this time to make it better. So the notation here, this is negative K and a negative K2, negative and a negative, and this is multiplication. This is the division, well, 1 over, or division and then multiplication part. So when we're trying to get this reaction 3, what we had to do is we had to flip both of these reactions and then add them together. So you flip both equations and then you add them together. And when you flip an equation, you are dividing part. You're not making it a negative. That doesn't quite work out. And then when you are going to add the two equations, you're going to multiply them together. So that's, I hope I answered that notation question that person had. Looking at number 8. Here's 8. This is one of the most common ones not to get right. So 8 I have over here. Okay. So when I think about this problem, I kind of think about it as, oh, that's terrible. I'm rewriting the equation, although it looks pretty terrible. So let's say I start with 10 moles of this and 10 moles of this, because it says equal number of moles of HCl and O2 are put inside there. So anytime you have the reaction go by, let's say one reaction goes by, in other words, one time the reaction happens, then suddenly I've got 4 less than 10, so I have 6 of these guys. One of these guys has gone away, so I have 9 of these, and I make 2 of these and 2 of these. Let's say another time the reaction goes by. After this, now I've lost 4 more of these. So now I have 2 of these. I've lost 1 of these because it has a 1 coefficient. That's 8. And now I have 4 and 4. So now that I kind of see what the system is doing, I'm going to look at my answers. If I look at 1, HCl must be less than Cl2. HCl is not less than Cl2. It doesn't have to be. It's 10 to 10 here, so that doesn't quite work. 10. Wait a minute. I'm getting confused. Sorry, I was getting confused with the O2. So number 1 can't be right because HCl must be less than Cl2, where my HCl here is a 6 and the Cl2 is a 2, so that doesn't fall eye with part 1. That's not true, especially if I look at my green lane or my purple lane. So O2 must be greater than HCl. O2 must be greater than HCl. That is true. This one is a true statement. Cl2 must equal H2O. Yes, these two are equal every time. That's because we start with only reactants. So that's why 2 and 3 are correct. Okay. Number 9. Okay. So at equilibrium, this equilibrium is put in there, and then you add more O2. If you add more O2, you add more to the product side. According to Le Chatelier's principle, if the product side is heavier or it has more on the side, it's got to shift to relieve that stress. It'll shift to create more of the reactants. So suddenly you have more O2, it'll shift to create more of the reactants, which means the SO2 will be used up. So the original equilibrium will have now, the original equilibrium is set, but once you added O2, you shifted it to create more reactants, which means you took away SO2 that was originally there. That's why there's less SO2 in the vessel now than there was before, because you added the oxygen. Number 10. Okay, so this one here is kind of tricky. You might have to reread it. But what it says is during the day, solar radiation absorbed by NO3 results in its decomposition. So in other words, during the day, you lose NO3. This goes away. So the reaction must shift to the left towards the reactants to create more of that NO3, which means you have a low concentration of N2O5 during the day. At night, the opposite is happening. At night, you're not losing this stuff, so you'll have more N2O5. The N2O5 will be higher at night because the NO3 decomposes during the day, which shifts it that way and decomposes N2O5. Now we're looking at 13. This one's a math one, kind of? Yes, math one. So, for this problem, okay. So for this problem, we're looking at KSP. So KSP is equal to the molar concentration of the lead times the concentration of the fluorine ions squared. So we're asking how many moles of NaF must be dissolved in 1 liter. So in other words, molarity of the F of a saturated solution of PbF2 to reduce the Pb to 1 times 10 to the negative 6. So right there, they tell me this is 1 times 10 to the negative 6. They want me to know what this X value is, and they give me the KSP is 4 times 10 to the negative 8. So here I'm solving for X. Now this is where you can't use a calculator because it's multiple choice, but on the free response questions, we'll be able to use a calculator. So I'm going to divide both sides by 10 to the negative 6. And I get 4 times 10 to the negative 2 equals X squared. I'm going to square root both sides, and I get 2 times 10 to the negative 1. Is that right? Yep. Which equals X. So that's equal to 0.2. So that is the molar concentration of F. And they're asking for the molar concentration of NaF, and this is a 1-to-1 ratio. So it's just the 0.2 molar. 0.2 moles per liter, or in this case, we're looking at moles, so it's in 1 liter, 0.2. Okay. And onward to 15. This one, they're just trying to trip you up with all the different numbers. They give you a bunch of different numbers, and at first I thought, oh, am I going to have to solve for KSP using those weird numbers? But no, and why they give me 0.9, that's not what it is. What it's really asking is to first Identify the molar solubility of CDF. Well, the KSP for this would be KSP equals a CD times the F squared. So the molar solubility would be the S, or in other words, the concentration of just the CD. And they told me that because they see this little teeny EQ, that means equilibrium concentration of CD. That means it's 0.0585. That's its S. So right there, it narrows it down to A and B. And then I can look at, well, if I'm going to add an additional NAF, this is just like Le Chatelain's principle. NAF would mean I'm adding F. More fluorine here on the product side would shift it toward the reactant side, which would mean I'd create more solid. And that's why A is the best answer. All right. And my last one is 16. Here it is. So this is talking about if you mix this in salt water versus not salt water. If you wanted to make it in distilled water, you would have a different value for the silver than you would if you had it in salt, and not in salt water, but tap water. So basically, the lab is trying to figure out, well, what is my Ag concentration here? So if I have it in DI water, you have a set value of Ag based on its KSP. But what if I use tap water instead? If I use tap water instead, that means I have some chlorine in there. There are chlorine ions in tap water. If I have some chlorine inside there, then it will shift the reaction to create more solid, more AgCl, which would mean overall I have fewer Ag than I did before. If I have fewer Ag than I did before, the KSP value that I would actually calculate would be less than I should actually have. So that's why B would be the best answer here. My KSP would be too small because there would be fewer Ag ions in the solution because the Cl has shifted it towards making more reactants. Shifting to make more reactants would mean I have fewer Ag ions. Fewer Ag ions, when I calculate my KSP, would mean my KSP would be lower because the number I would get from my Ag out of this lab procedure would be less than it normally should be. Okay. I hope I solved them all and not too fast. Yeah. Here's your bonus for the end. I have puppets. Oh, this one's very sad. This guy's name is Flossie. Hello, I'm a puppy and I'm Flossie. There you go. Color this one. And here is, it's a ram. Flossie's gonna go around the ram. I could not think of anything for tonight. I'm so sorry. Here's your stupid puppet show. I'll do better. I promise. Good night.